So in today's class, we shall understand simple harmonic motion and uniform circular motion. So in this class, we show that the projection of uniform circular motion on a diameter of a circle follows simple harmonic motion. So let me draw a figure. So now if you look at the figure, a simple experiment helps us to visualize this connection. So let's say you tie a ball to the end of a string and you make it move in a horizontal plane about a fixed point with a constant angular speed. And the ball would then perform a uniform circular motion in the horizontal plane. Now you observe the ball sideways or from the front, fixing your attention in the plane of motion. So the ball will appear to execute to and fro motion along a horizontal line with the point of rotation as the midpoint. So you could alternatively observe the shadow of the ball on a wall which is perpendicular to the plane of the circle. So in this process, what we are observing is the motion of the ball on the diameter of the circle normal to the direction of viewing. So if you look at this figure describes the same position mathematically. Suppose a particle P is moving uniformly on a circle of radius A with angular speed omega. The sense of rotation is anti-clockwise and the initial position vector of the particle, that is the vector OP bar at t is equal to 0, makes an angle of phi with the positive direction of x-axis. So in time t, it will cover a further angle omega t and its position vector will make an angle of omega t plus phi with the positive x-axis. Next, consider the projection of the position vector OP on the x-axis. So this will be OP dash and the position of P dash on the x-axis as the particle moves on the circle is given by x of t is equal to a cos omega t plus phi. This is the position of P dash, which is the defining equation of simple harmonic motion. So this shows that if P moves uniformly on a circle, then its projection P dash on a diameter of the circle executes SHM. So the particle P and the circle on which it moves are sometimes referred to as reference particle and reference circle. So we take projection of the motion of P on any diameter, let's say y-axis. So in that case, displacement y of t of P dash on the y-axis is y is equal to a sine omega t plus phi, which is also SHM of the same amplitude as that of the projection on x-axis, but differing by a phase of pi by 2. So in spite of this connection between circular motion and simple harmonic motion, the force acting on a particle in linear simple harmonic motion is very different from the centripetal force needed to keep a particle in uniform circular motion. So let me give you some extra information. So the natural unit of angle is radian, defined through the ratio of arc to radius. So angle is a dimensionless quantity and therefore it is not always necessarily to mention the unit radian when we use pi and its multiples or submultiples. So the conversion between radian and degree is not similar to that between meter and centimeter or a mile. So if the argument of a trigonometric function is stated without units, then it is understood that the unit is radian. And on the other hand, if degree is to be used as the unit of angle, then it must be shown explicitly. For example, sine 15 degrees we have to write. But if we are writing in radians, sine pi by 6 is enough. Here radian is not necessary. Okay. So these are the rules between degree and radian. So this is an example. The given figure depicts two circular motions. The radius of the circle, the period of revolution, initial position, and sense of revolution are indicated on the figures. We need to obtain the simple harmonic motions of x projection of the radius vector of the rotating particle in each case. So first let us start with the first case. So in the first case, at t is equal to 0, if you look at the first figure, OP makes an angle of 45 degrees. 45 degrees is pi by 4 radian with the x-axis. That is positive direction of x-axis. Now after time t, it covers an angle 2 pi by t into t in the anti-clockwise sense. And makes an angle of 2 pi by t into small t plus pi by 4 with the axis. Capital T refers to time period. Now the projection of OP on the x-axis at time t is given by x of t is equal to a cos 2 pi by t into t plus pi by 4. And for t is equal to 4 seconds, x of t is equal to a cos 2 pi by 4. In the place of capital T, we put 4 into small t plus pi by 4, which is a simple harmonic motion of amplitude A. Period 4 seconds. And initial phase that is equal to pi by 4. This is for the first case. Now let us see for the second case. Now we shall do it for the second case. So look at the second figure. So in this case, at t is equal to 0, OP makes an angle of 90 degrees. 90 degrees is pi by 2 radian with the x-axis. So after a time t, it covers an angle of 2 pi by t into t in the clockwise sense. And makes an angle of pi by 2 minus 2 pi by t into t with the x-axis. and the projection of OP on the x-axis at time t is given by x of t is equal to b cos pi by 2 minus 2 pi by t into t. That is equal to cos 90 minus theta is sin theta, right? So we write sin 2 pi by t into t. Now for t is equal to 30 second, x of t is equal to b sin pi by 15 into t. We take capital T as 30. So 2 and 30 will get cancelled. So writing this as x of t is equal to b cos pi by 15 t minus pi by 2 and comparing with the equation, we find that it is SHM of amplitude A, of amplitude B, period 30 second and initial phase of minus pi by 2. Now let us continue with velocity and acceleration in SHM. So if you look at the figure, the speed of a particle is given by v in uniform circular motion. So speed is its angular speed omega times the radius. So that means v is equal to omega a. So what do you mean? The speed of the particle in uniform circular motion is omega times the radius. And the direction of velocity, that is v bar, at a time t is along the tangent of the circle at the point where the particle is located at that instant. So from the geometry of this figure, it is clear that the velocity of point of projection p dash of the particle p at time t is v of t is equal to minus omega a sine omega t plus phi. Here omega t plus 5 is the angle, where the negative sign shows that v of t has a direction opposite to the positive direction of x-axis. So this equation, it gives the instantaneous velocity of p dash treated as a particle executing SHM, where displacement is given by x of t equals a cos omega t plus phi. This is displacement and this is velocity. So we can of course obtain this equation without using geometrical argument directly by differentiating this x of t with respect to t. So you will get v of t is equal to d by dt of x of t. That is equal to d by dt of a cos omega t plus phi. So the method of reference circle can be similarly used for obtaining instantaneous acceleration of a particle undergoing SHM. So we know that the centripetal acceleration of a particle P in uniform circular motion has a magnitude of v square by a or omega square a, and it is directed towards the center. That is, the direction is along PO, and the instantaneous acceleration of the projection particle P dash is then A of t equals minus omega square A cos omega t plus phi. So that is minus omega square of x of t, because A cos omega t plus phi is x of t. So this equation, it gives the acceleration of a particle in a linear SHM. So the same equation can again be obtained directly by differentiating velocity. Over here we have velocity vector, right? If you differentiate velocity, you will get acceleration. So A of t is equal to d by dt of v of t. So we can see that from this equation, from A of t is equal to minus omega square x of t. From this equation, we can note that the important property, that acceleration of a particle in SHM is proportional to displacement. So for x of t is greater than 0, A of t will be less than 0. If x of t is positive, then A of t will be negative. And if x of t is negative, A of t will be positive. So if position is positive, acceleration will be negative. And if position is negative, acceleration will be positive. Thus, whatever the value of x between minus a and a, the acceleration A of t is always directed towards the center. So for simplicity, let us put phi is equal to 0. And we will write the expression for x of t, v of t and a of t. So x of t will be a cos omega t, because we are putting the phase angle as 0. And v of t is minus omega a sin omega t, and a of t is minus omega square a cos omega t. So if you plot a graph, you get displacement like this. This is displacement. And this is velocity. And this is acceleration. This is for acceleration. So these are the three different plots. So all the quantities vary sinusoidally with time. Only their maxima differ, and the different plots differ in phase. X varies between minus a to plus a. V of t varies from minus omega t to omega t, and A of t from minus omega square a to plus omega square a. So with respect to displacement plot, velocity plot has a phase difference of pi by 2, and acceleration plot has a phase difference of pi. So let us take an example. A body oscillates with SHM according to the equation x equals to 5 cos 2 pi t plus pi by 4. So at t is equal to 1.5 second, calculate. We need to calculate three things over here. One is displacement, the other is speed, and the other is acceleration of the body. So this is a numerical. So let's see how do we solve it. So what is the angular frequency? Angular frequency omega is equal to 2 pi per second. And its time period is 1 second. So at t is equal to 1.5 second, let us first find out displacement. So displacement is 5.0 meter into cos 2 pi per second into 1.5 second plus pi by 4. So that is 5 cos 3 pi plus pi by 4. So that is minus 5 into 0.707 meter. So that will be, if you multiply these two, you get 3.535 meter. This is how we found displacement. Now we will see how to find out speed. So speed is equal to minus omega a sine omega t. So you get minus 5 into 2 pi sine 2 pi into 1.5 plus pi by 4. So that is minus 5 into 2 pi sine 3 pi plus pi by 4. So that is 10 pi into 0.707. So that is 22 meters per second. This is the B bit, that is speed. Now C bit is acceleration. What is the formula for acceleration? It is minus omega square a cos omega t. So that is minus 2 pi per second whole square into displacement. So that is minus 2 pi per second whole square into minus 3.535 meter. That is, if you multiply them, you get 140 meters per second square. Now let us see what is force law for simple harmonic motion. So using Newton's second law of motion and the expression for acceleration of a particle undergoing SHM, the force acting on a particle of mass m is F of t is equal to ma. That is minus m omega square x of t. Because we know a is minus omega square x of t. So f of t is equal to minus k x of t, where k is a constant and k is m omega square. So from here we can find omega square as k by m and omega as root over k by m. So like acceleration, force is always directed towards the mean position. Hence it is sometimes called the restoring force in SHM. So to summarize this discussion so far, simple harmonic motion can be defined in two equivalent ways, either by uh, displacement or by force law. Okay, so we can differentiate it two times. Likewise, we can integrate the force law two times. So we get the equation. And also you note that force in this formula is linearly proportional to x of t. So a particle oscillating under such a force is called as linear harmonic oscillator. So in the real world, the force may contain some additional terms proportional to x square, x cube and so on. So these are called as non-linear oscillators.